Okay guys, we're going to start. Um, Today's topic is intelligent agent architecture. We will talk about how to design something as an intelligent agent. So in each of the slides you will get some of the concepts related to designing an intelligent architecture. You saw this slide from the previous class. This one is talking about an intelligent agent, and then if you consider the example of this one as a serving robot here. So we have a serving robot, and then we can consider this one as our intelligent agent that can interact with the environment to provide us some service. So what can be the attributes here? You saw all these things before: abilities, goal and preferences, prior knowledge, observations, past experience. These are the attributes related to intelligent agent. But if we consider this, these are the names actually. And then for all these names you can have some values when you consider this one as your intelligent agent. If you consider instead of a serving robot maybe another example, maybe a medical diagnosis robot or something like this, then you may have this kind of, you may have different values for this kind of names. And when we are talking about these names, there is some term in artificial intelligence to use these names. We will discuss this one later. First, just see here. We have the name as abilities. What can be the abilities for this robot? We have movement, grippers, speech and facial expressions. And then we have goals. We have prior knowledge for this one. And we have observations and we have past experience. And these two slides actually you have seen before in the last class. So, and that is our starting point today. We want to design an intelligent agent, and what will be the key concepts in designing that one. So when we have this one as an example, serving robot with the attribute names and then with the values of the attributes, then the first thing in designing an intelligent agent, or in just going through the process of designing an intelligent architecture, the first thing is understanding the domain. What does that mean? Understanding the domain. To understand the domain, you can consider this one in this way. Say we have serving robot, and we have a map where the robot will serve. Say for example, this robot will serve coffee to me. So the robot need to know where is the kitchen. Where can it get the coffee for me? And then the robot need to know where is my office. And then the robot also need to make the decisions what route it should follow. And then there can be some obstacles also in the route. For example, it is going in the corridor and then somebody is walking in front of it. That can be a situation. So these are different situations we can see, or different scenarios we can see while this serving robot work in an environment. And when we want to design something, the first thing is realizing all these scenarios. And that is we are telling domain understanding. And I just put an example here if the robot want to serve something to me. So when we are trying to understand the domain, then what is our objective? The objective is designing that one, that intelligent agent. And when designing that thing, we have to consider these 4 points. First of all, modeling the environment. The environment the agent will work. If I am an agent in this classroom, I am not the environment. The environment is the classroom. I am the agent who will work on this one. And then evidential reasoning and perception. I have to have some logical reasoning thing in my brain state or in my controlling, so that I can interact with this environment. The environment will give me something. Using my sensors, I can take those things. And then I have to perceive something. I mean, based on sensory input, I have to understand something about the environment. That is perception I'm taking. And then when I'm doing these things, I'm using some kind of logical things which I got in my brain state or in my controlling system. So that is the evidential reasoning and perception. We have observations, and based on the observation, we can understand what the environment is looking like now, or what are the state I am in now. States. So then, next thing is action. If you consider my example, or if you consider the serving robot example, it is nearly similar. We have to do some action. I have perception. Based on sensory input, I can take the I can make the perception, and then I have to do an action. So what is the action? Given a model of the world and a goal, determine what should be done. So right now, what is the environmental situation that was given? And maybe the goal is what? Goal is just turning on the switch maybe. So then I have to make the action. I have to work through here, and then I have to push the button, something like this. And then the last thing is learning from past experience. When I do this one, then I got an experience also. I provided the service, but beside this I got an experience. So, and this is, I can input in myself again to make this one valuable information as a knowledge base for my future actions. This is the last thing, learning from previous experience. So we are understanding the domain, and then these are the common tasks in domain understanding when we want to design an intelligent architecture. Do you have any question on this? Okay, good. Then, as you see in these 4 common tasks, if I ask you to do something related to all these 4 common tasks for a serving robot, or for a teacher in a classroom, or for a student in a classroom, all of us are agents here. So if I ask you to do some brainstorming on these 4 tasks, you will see that obviously all of you will not come into the same point after brainstorming. All of you will not get the same understanding of all these 4 points in the same way. For action, maybe somebody will define action in one way, somebody will define action in other way. So at the end, when designing an AI system, we always have some assumptions. And also we have some limitations. So we cannot always make a system what we like to make in the way that it can do everything related to a task or something like this. We always have some limitations. Maybe computational resources are not well enough. Maybe we do not have enough funding. Maybe the environment has some other restrictions which we cannot change. All these restrictions we can have. These are the limitations, and we have to consider those things. So that's why we have some assumptions before developing something. What kind of assumptions we can have for serving robot?
It doesn't have to walk up the stairs.
Sorry?
It doesn't have to walk up the stairs.
Yeah. Anything else? What kind of limitation we can put, or assumption we can put that okay, this will not happen, so robot need to understand that one.
The coffee will be ready.
So it doesn't need to make it. It can just get this one ready.
Yeah. So it's
So then you don't have to handle the making things in the robot. Okay, then what else we can get?
All doors are open. All doors are open.
All doors are open. Yeah, that is important. If doors close, what we need to do. And then what else we can get? You already took one chance. There is only one life here.
There won't be any obstacles in the start.
Yeah, that is true. And then
So-
anything else?
You can assume something about the mind, since people, working in the office.
Yeah. So actually, the more we think, the more assumptions will come. And then the basic idea is research proceeds by making simplifying assumptions and gradually reducing them. At the beginning, we always start by a simplified system. We don't want to handle all this complexity from the beginning. So we make some assumptions. Okay, this will not happen, this will not happen, this will not happen. So the boundary is very limited. What we have to do, just within this boundary. What the robot need to do, just maybe walking from this place to that place, and then moving the hand to give something. No other challenges. And then you will increase the complexity by removing those assumptions gradually. This is the way to develop something, an intelligent agent. But when we are considering about assumptions, we have to put the assumptions on the context of that intelligent agent, related to its environment, related to its control structure. How will you design those things? When you put the assumptions, we have to put those assumptions on those concepts. What are the concepts related to these assumptions? These are the concepts, and I will go each of these concepts one by one in the next slides. You can just have a look. Modularity, planning horizon, uncertainty dynamics, sensing uncertainty, single and multiple agent, learning from experience, and limited rationalism. Actually, this is not a limited list. You can include many other things here. But I just bring here some of the important concepts so that you can just keep in your mind while designing the system. So first thing is modularity. What does that mean? This is not about the environment. Of course, you can put this one in environment, but this is about the agent itself. In this class, there is a teacher, for example. So, and teacher is the agent, and you want to develop something like this, a robot teacher, something like this. Or we can consider our normal example as starting robot, regular example. So these things, modularity, is related to the architecture of the agent, not the classroom or the environment. How it will work? Flat, modular, and hierarchical, these three alternatives we have in terms of modularity. Normally, if you, all of you already did some kind of programming, so you know something related to programming. What does it mean by sequential or flat design of a program? And then you know something about why are you laughing? Is that interesting? And then you will get something related to modular approach, and then you will get something related to hierarchical approach. So, but it is not exactly similar in programming, because in programming we have three concepts. One is flat, another one is modular, and the third one is object oriented. I mean, it is not exactly object oriented. There is another name, anyway, I cannot remember. But in this case, flat means when your agent is very simple. Say for example, you want to go from this place to Paris. What can be the steps? Just go from Aalborg to Aalborg station, here to Aalborg station to maybe Copenhagen, and then take a plane and then go to Paris, finish. You have to put a lot of assumptions also that okay, you will get a train. So then you have to make the assumption that the plane will not be delayed or something like this, because every single step will make more complexity. But a flat design can be like this, simple one by one step and no other branching and everything like this. But what is modular design? In modular design, the agent can be like this. There are many blocks in the agent, and then if you put together, that is your whole agent. And then what is hierarchical? In hierarchical approach, actually it is more similar to our approach, the way human beings are made. You see, in our approach, all of our organs are necessary, it is true. But all of these organs are not necessary in the sense of our survivability. I mean, you cannot survive without brain, you cannot survive without heart, but you can survive without a hand organ. So there are some, all of these modules are not in the same level. So you put in a hierarchical structure to define those things. We are telling that that can be hierarchical. So designing of an agent, is that flat? Is that modular? Is that hierarchical? It is actually depending upon our way of defining the thing. There is no fixed thing that you have to define this one in a hierarchical mode. No. It is we define. We want to see which way is better representing our system. I'm just telling that these are alternatives available in front of us. We can design in this way or that way. Yes?
I don't really see the difference between the modular and the hierarchical.
Yeah, in some way no difference. Except the thing that in hierarchy, we see a hierarchy like this. And in modular, I didn't put the hierarchy like this. That is the difference. But normally, actually, without making module, you cannot make the hierarchy. So in that way, all the hierarchical things also have modular elements. Yes.
The three figures in the top, do they represent flat, modular, and hierarchy? Or what are they for?
Which one?
The three figures in the top sequential.
This is just about the flat design. In flat
Okay,
design,
that's
actually,
just-
what we do, we just go for example, like this, one by one step by one step, and like this, and then we can make some conditional branching that if this is not, we will go like that, something like this. But all of these things you can put in hierarchy in the flat design, because this is a simple thing. You don't have to divide the whole problem area into multiple blocks and then solve each of them separately and then put together. That is the way of modular thing. I will take the question just a moment. So, if you can remember, when you write a function in C programming or some other programming language, what did we do? We have a big problem, and then we just write one by one line code, and then we can finish. So, for example, making a calculator, you don't need to write many functions. You can do all these things in one program or one function. And then now you are thinking that no, I will not go for this kind of flat design, I will go for modular design. What can be that? Then you are putting that, okay, if this is addition operation, one thing will do this, one block of the system will do this. If it is multiplication, another block will do this. And then it will handle all the complexities of multiplication. If it is division, another block will do this. What can be the complexities for that block? For example, you can add, subtract everything using a zero number, but you cannot do division when zero is on top. Is that zero? No, zero is under the line. So division operation need to take care of that, which addition or subtraction don't need to take care of those things. So these are the ways you can break the whole thing into multiple pieces and then put together. That is we are telling as modular. And then in the modular approach, after that you can put this one in hierarchy depending upon your system if you need more clarity on that one. Yes.
So programming the modular would be object oriented, or somewhere around that?
Actually, when we define module, if you consider the programming approach, then we actually focus on the processing, and we divide the task. This block will do this task, this block will do this task. But when we consider object-oriented programming, actually we do not talk about processing. We talk about the data. We divide actually the data. These data will not be similar with this kind of data, and then we are blocking those data. This is one block of data, this is another block of data, and then we are putting the processing with the data. That okay, this data will be processed by these things, and this data will be processed by these things. If you can remember, in object-oriented programming, you create a class, there you will put the variables, and then you put the methods or the functions to process those variables in that class. So the focus is on data abstraction. Focus is not exactly processing. But in modular approach, the focus is processing. Why these things are happening, that is actually even bigger discussion. But the way we deal the real world, this is more object-oriented, not modular or simply flat model. Then you can think in your mind why this is like that. So next thing is planning horizon. The basic idea is how far agent looks. And it can be in 4 dimensions. One is static, another one is finite stage, another is infinite stage, and the last one is indefinite stage, and last one is infinite stage. So when the agent thinks that the environment, the world means the environment where the agent is reacting. For example, the classroom. Is the classroom static? For our case, actually, classroom is not static. Some students is going in, some students are going out, and then there can be less student in one class, more student in another class, and the class environment is changing. One day you are presenting something, one day I am presenting something, and sometimes when you ask question, it is just a random question. Who asked? I don't know. So all these things indicating that this is not static. The world is changing. And then finite stage. The way I explained this one, the first one, the world is not static. Do you think that we have a stable number or fixed number of states in this environment? Or we actually don't know how many states can arise here in this class? Do you understand that how many states we can get, different states we can get in this classroom? How many different states we can get? I actually exemplify some of the states when discussing about static mode, that we are not having similar states, so this is not static. But how many states in this class we can get?
How many steps?
States.
Steps.
Yeah, just think this one with the static concept. Is this static? If you understand that no, this is not static. Why? Because the states are changing. It is not fixed. Somebody is moving here and there. You are talking out, somebody will tell hello from other place, or somebody will smile. So it is changing continuously. And I am not reacting in the same way when you are reacting also. So it is continuously changing. It is not static. Is that clear? Yes.
What was the agent we were talking about in this case?
Now, say for example, I am teacher. I am the agent.
Okay.
And the classroom is the environment. I'm sorry for mentioning that. Yes.
So because let's say that the scheduled time is a part of the environment, the stage or the amount of stages will also be affected by the available time for the
So you are
environment.
telling that there is another dimension of time, because on time it is changing. It is true.
But in that case, then because this is a course which has a finite end of time as well, would that mean that the amount of stages will also be a finite amount?
If you consider that there will be an end of time for this, then it is right. For this class, it is 3 hours, or 4 hours, or 2 hours. Then at the end of 2 hours, we know that there will nothing happen. There will be anything. There will be nothing to happen. Yes. What you are asking? Okay. Yeah. So, if you understand the concept of static, then it will be easy to understand the concept of finite stage. It is not static because we are changing the states. Then what does it mean by finite stage? It means that total number of states, different states we can get from this environment is fixed. But can we really define? For example, if I tell you to design an intelligent robot like this who will just deliver the lecture, is this really possible to limit this one that the number of states will be like this? It is not an easy work. Exhaustively we can search. Theoretically maybe it is possible to find out all the states, but practically it is extremely difficult because every single of you are a student agent, even though I am a teacher agent. When you are talking about teacher agent, there are student agents who are also intelligent agents, and they can strategically define their way of actions, and which is actually changing the environment in an uncertain way, which I don't know exactly. So from my point of view, I cannot actually tell how many states can happen here. Yes.
Oh, yeah, that's-
You understand
No,
that?
It's because we can ask questions, right? So
Yeah.
if we didn't have the ability to ask questions, it could be finite because you have your predetermined.
Even then there will be other problems also. For example, I'm not only taking questions, I'm also taking your expressions.
Oh, okay.
So if we were smart agents, then
Yes.
But even so, that would still be a highly philosophical question, because that still depends on whether you believe time is predetermined or every single event.
Yeah, there are some complexities like this, because as I told you, theoretically maybe it is possible to explain everything, because maybe nothing is random in this world. The way you are reacting, maybe I cannot explain all these steps or which steps you will follow in your reaction, but maybe there is some way to address all these things. I'm not going that kind of highly philosophical things. I'm just telling that overall, as a teacher, in overall concept, I actually cannot predict how many states can happen here. It can be many. So that's why maybe I'm assuming that I cannot go for all these things, because when going to these slides, I told you that why we are discussing this, because we have to assume something. There are complexities related to these concepts in designing an intelligent agent. So we have to assume something. We have to limit the space for the agent. He cannot do everything. I am a human being. So I am not only taking your question or giving the answers, and depending upon answers, maybe you will ask another question based on answer, not based on the slide, maybe. So all these things are variable concepts. But I'm also, if you do not ask any question, still I'm taking your emotional states or mood. Now emotional state, facial expression, they are also different things. They are also not the same things. So everything is complex, but as a human being, I'm processing all these things. So if you consider an intelligent agent, maybe we cannot put all these things in an agent. Because we don't have maybe enough knowledge base to put into the inside of the agent. Even the knowledge base also are not same, even for human agents also. If I am a teacher and he is teacher, it can be different scenario. So everything is complex. The idea we are telling that either the world is static, we can assume this one, or we can assume that the world has some finite number of stages. Finite number of stages. Or the world can have indefinite stages related to time domain. Or the world can have infinite number of stages. We cannot say how many steps and which time or everything is relaxed now, open now. The world can be like this. But when we design an intelligent agent, maybe we cannot design for this one. So we have to put some assumption on this. Okay, the world will not be like this, I'm assuming. I will show you a video. In that video you will see that how experimentally some students are making a robot, serving robot, and how it looks like. They put even the line on the floor. Why? Because they don't want to handle other complexities. The robot will just capture the black line and then go on that line. I mean, they are assuming, they are putting the assumption that the road will have a black line. Why? Because this is the easier way to make or design that agent. And that is the starting point for them. I will show that video to you. So this is we are planning horizon. How much the agent will think about the context. Is that changing or not changing? Is that changing over time? Or is that continuously going on indefinitely? And we don't know how many number of steps, we don't know. These can be different situations. And then uncertainty dynamics. What is uncertainty? I asked you this one maybe in the last class, but do you have any answer about this? What is uncertainty? Yes? That's me.
It's when there is no clear possible evaluation that will lead to a certain outcome or state.
There is no possible evaluation.
The lack of information is probably a better way to phrase it.
Yeah, that is good. Yeah. What is your answer?
Possibly if the agent has two different outcomes to a certain scenario, so it doesn't know which one might be the case, so it could be a certain level.
And maybe in its knowledge base also isn't giving it any bias to which direction it should go. Then it will have an uncertain state of making decision. It is true. So uncertainty occurs mostly due to lack of information. Just like this, you don't know where to go, something like this. And then when designing intelligent agent, how the concept of uncertainty affects us. First of all, two things. There can be no uncertainty in the environment of that agent. I'm the agent, this is the environment. And there is no uncertainty here. Because I know nearly everything of this, every single steps I can predict, so there is no uncertainty. Another way is there are uncertainty, and then when there is uncertainty, then we can have actually many different definitions of uncertainties. Among these, I just bring one example, probabilistic uncertainty. Maybe there can be 10 different states happen in this classroom. Only 10 static, okay? 10 different states. But this state is less likely than the other one. You already read about probability and all these things in design and analysis of experiment also. So what is more likely and less likely, you understand that difference. So maybe this event is less likely, this event is more likely. So this is we are telling us probabilistic uncertainty, that the computer or the agent, as an agent, I don't know exactly what will happen, or I am still having difficulty to decide, but I am now calculating that this is more likely and this is less likely among two different states. So there can be a distribution of probability between the states. So one is no uncertainty, I know everything and I know exactly what will happen and how, in which degree, everything I know. Another one is there is a probability. So you know, in probability, if you say 100%, does it mean that it will happen? If you say 100%, it will happen, does it mean that it will happen? In probability.
Yes.
Yes.
I don't think you can
So-
say that
Certain sort.
it's 100% probable, because there's always the chance that something comes up and
What you
I mean, it would be based on your information, but if your information is really wrong, then obviously it doesn't happen. So it could not happen. in case.
Yeah, that is true. Yes.
It will be an inbuilt problem with proving something 100% probable. Because 100% probable is not a problem, then it's certain.
Yeah.
then
Yeah, there is a
no-
concept like this in design and analysis of experiment. We studied that one also. That what is certainty and what is probability. Sometimes when if you consider all the possible things and theoretically possible things, you have considered everything, and then you are putting that okay, this is 100% possibility. So if it is 100% possibility based on your all the possible knowledges you can gather, then you can tell this one as a certainty for your case. But anyway, I'm just telling okay, let's say 99%, not 100%. Does it mean that in 100 trial you will of course get one as not happening? No. This is because it is probability. So when we are telling probabilistic uncertainty and no uncertainty, it means that no uncertainty case, the agent knows everything. It knows the degree exactly and it will happen like that. In probability is also giving a degree of certainty, something like this. How probable it will happen. But it is not certain exactly. Even in 99% case, if you give 100 trials, maybe one trial will not fail. That trial can also be a successful one. I mean, you can get in the result 100% success. But probability can tell that okay, there will be a failure case of 1%. I don't know whether you are realizing this one, but it is just simple. No uncertainty or some kind of uncertainty. And then when you are considering uncertainty, there are two dynamics. One is deterministic, another one is stochastic. What is deterministic? If you realize deterministic, the opposite is stochastic. Okay? What is deterministic? I am an agent and I want to decide something. I got the environmental status that the environment is now like this. Now will I turn on the light, or will I turn off the switch light, or will I move the window, or will I just deliver the lecture continuously? I am deciding this one within myself. Based on this state, I am deciding something. Now, am I actually, what can I tell? Deterministic. Do you understand this term? I don't know whether you are understanding this. Am I confirmed that I will do this one exactly? Nothing else I will do. Based on this situation. For example, in this situation, I will maybe continue talking. Or maybe suddenly I will go there and then tell that okay, light is not enough for me. Will I change the light? Something like this. So my decision, am I confirmedly know what will I going to do? What will I do? I do something like this. You want to? I don't know. Your answer is that. So this is the thing. In deterministic matter, we know exactly what we will do based on the situation. But in stochastic matter, it is opposite. We don't know exactly what we will do. Even the situation is given. And why it is happening? Because even though the situation is given, but still I have some unknown things and I have some uncertainty. That's why I don't know what will I do exactly. Two players are playing chess. Chess game, do you know chess? Who don't know this? Who doesn't know this? Chess. Chess game. Everybody knows. So it is a good example then. Playing chess. You have a computer which is not as intelligent to improvise something. I mean, it is not changing its knowledge base. It is just doing the math and then moving the board pieces. And then you have another human being. Maybe he knows less or more of that game anyway. But can you exactly predict what will he do? Yes.
No.
We don't know. But for a machine, you can do that. But if the machine has the ability of improvisation, I mean changing something on its own randomly, then can you guess now what the machine will do? Just say it, no problem. We cannot guess exactly because we don't know which random state this machine will take now. But why at the first time we are able to tell this? Because we know that the machine will not do any kind of random state. It will do the best one. And if we know the best one, and then we know the states, finish. But actually chess is a complex game, so we don't know exactly what is the best step in a specific scenario. There can be multiple best steps, all are equally probable. So anyway, I'm just telling that in a deterministic system, we exactly know what we are going to do based on the situation. In a stochastic system, there are some uncertainties available. So we cannot decide exactly. Our decision based on some other things also. While designing an intelligent agent, you have to consider these things, actually for which environment and what type of agent I'm going to design. That is the idea, yeah. Then sensing uncertainty, yes.
About the agent creating, making, or evaluating the agent environment interaction. We have, let's say, a dynamic situation. Some of it might be, should some of it like be deterministic and some of it's stochastic in that sense that it doesn't necessarily have to be like the entire agent that act like it could be different substates.
That is true. Actually, all these concepts we are talking about, it is not that when you are going for a stochastic, there is no deterministic element. No, there can be some deterministic element also. When you are going for deterministic, it doesn't mean that there will be nothing stochastic here. You can maybe assume that I will not consider the stochastic scenario now, just to limit or make it easier for you to develop the thing. But at the end, all these things can be mixed up. In a hierarchical design, you will of course have inside of it some flat designs. Because hierarchical concept we develop only to explain a complex system. For example, we have a student group here, 5 or 6 persons sitting together and talking with each other and designing something. This is kind of flat design. Here nobody is superior or nobody is lower or something like this. But then, for example, you are going to a company to do a job. Then you have a group and you have a group leader, and then there are some other hierarchies also. I mean, bigger managers also. So then we are going for a hierarchical design just to make it scalable. So when we go for big things, we have to explain and think the matters in that way. So anyway, sensing uncertainty, we talked about deterministic and stochastic matters, and then now you see when you have uncertainty, then there are two options available. One is fully observable, another one is partially observable. So theoretically, maybe it is possible for a teaching agent that he can predict all the single steps here, or he can understand how many number of steps can occur here. Maybe theoretically, let's say, though it is also a matter of debate. But let's say I know all the steps, and I know how he will react, and I know how he will react. I know all these things. Then all the information is visible to me, and I can observe that one. Then it is we are telling us fully observable. But it is not true that we can see all the information in a classroom. It is true. Is that right? It is not true that we can see all the information. So what is happening here? It is actually partially observable scenario I am getting here. Partially observable scenario I am getting here. This is, we are telling how we sense the uncertainty here. When it is partially observable, I don't know something. And when I don't know something, uncertainty is coming there. And sometimes it happens that I know something, but still uncertainty can come because maybe the state space is infinite. I mean, there are infinite number of steps, so I cannot exactly put word for every single steps. Yes.
Would that mean that whenever you have something like an infinite number of states, it will never be capable or never be possible to have a fully observable scenario?
No. This doesn't mean like this. Because in science it is very difficult to say it is impossible, or it is very difficult to say it is always possible. I mean, we cannot go for extreme things. So every day we are improving and we are solving something which we didn't know the solution yesterday. So we have these two options, fully observable or partially observable. We can get those two options in case of uncertainty sensing. I think we have two more slides related to this. Then we are having single and multi-agent system. Is this classroom is a single or multi-agent system? Just tell from your common sense. Multi-agent. And why multi-agent?
Because we're multiple people.
We are multiple people. Only because of that? Yes?
As long as there's anything that can act on the environment and act upon environment tool changes, there would be an agent. So every time we have a piece of equipment that we can interact with, we would also have an agent on top of that.
Okay, yes.
Also with different roles, with the teacher and student and all that.
So different roles are making different agent. Okay. So this is a multi-agent system. So from common sense we are understanding that. That's why I don't need to explain so much. In multi-agent system we have multiple agents working in the environment, and if you want to design me only, you cannot just design me without understanding of all other agents, at least a bit. So in a multi-agent system, this agent will make its decision based on a strategic understanding of the other agents. That is the concept in multi-agent system. And in single agent system, it is just only one agent and every other things are static. No intelligent agent is working here anymore. For example, what you can say? Let's say nobody is here. I'm just coming here. I have just come here in this room and just I want to read something. And I'm an agent who will do this work. So everything is nearly fixed. If there is no light, I can put the light. If there is little light, I can increase the light mathematically by mathematical calculation or something like this. There are chairs available, maybe I can go for the chairs and something like this. So it can be a single agent system sometimes. And sometimes it can be a multi-agent system. In multi-agent system, maybe we are not designing all other agents. All other agents may be available, but we are designing one agent, and then we have to consider those agents who are in the environment while deciding something for this agent. For example, for serving robot will serve tea to me or coffee to me. Then the person who is designing that serving robot, he is not designing me. He is designing that serving robot. So that serving robot need to understand something about me. It is not me who should understand something about that robot at the beginning. Yeah.
You've written that reasoning through an agent assumes that any other agents are part of the environment. Does that mean that the environment doesn't affect us, or what does that mean?
Environment of course affects us. But environment doesn't have other intelligent agent with which I have to make the decision in a strategical point of view. If this is a table fixed here, there is no strategic decision making. This is just mathematical decision making. The table is here, I can sit here, and then I can read, something like this. But if it is a human being, as I told you in the previous example, in chess playing, if it is a machine and you know that it is just doing mathematical calculation very straightforwardly without improvisation, I mean without changing intelligently something or randomly something, then you know what it is going to do after this move. But so you don't have to consider this one as a multi-agent system. But while you are considering that there is another intelligent agent, then you have to make some strategic decision between the agents. Maybe I should be here in the room, but I am here in the room. Then if the robot come and serve here, he will actually not get me here. He need to understand that I can move. So I can move, this understanding is just giving him the concept that there is another agent and I have to depend on that one. So normally in most of the cases we do not get actually single agent that much. Most of the cases we have multiple agents. But in designing perspective, we do not actually consider multiple agent that much. In gaming you have an opponent. But in serving tea also you have somebody who need to take the service. But in just starting in a static room, maybe we can consider this one as a single agent system. Even though we can argue that that can be also multi-agent system, because somebody is cleaning the room in the morning and you don't know how he is putting the room. So the arguments can come like this, but the overall idea is that in a single agent system, the agent does not rely on other information in a strategic point of view on other agents. I mean the decision of other agents on a strategic point of view. But in a multi-agent system, agents actually rely on the decision of other agents in a strategic point of view. For example, in gaming, this is a multi-agent system. You have an opponent and you are playing. Maybe the opponent is a computer, but still you are playing with him and you are making a strategic decision based on his decision or the other counterparty's decision. That is the idea. Is that clear? Single and multi-agent. Yes.
Does that mean that we theoretically could perceive single and multiple agents from the point of view of an agent in that system? So from one point of view, one agent might be a single agent in the environment, and from another point of view, you could have something that would be a multiple agent.
There can be this kind of point of views, but while designing or developing, or when you are writing a code for something to process, normally you are going for one specific decision. That okay, I'm assuming this is not happening, so I'm going for that. And I'm assuming this is happening, so I'm going for this condition, something like this. So as a whole, actually, as I told you, single agent, multi-agent and all those concepts are not limiting that one system will be always multi-agent or single agent. That system can have many different dimensions. But based on one iteration of your development, maybe you are putting the assumptions that I'm considering this one as a single agent system now, and that's how I'm making the decisions, and I'm developing the system in that way. This is just in your design process. You can just think in your mind which way you will go. So normally, the plain understanding is in a multi-agent system, you have multiple agents whose decisions are actually linked with each other. Those decisions are linked with each other. So I cannot take a decision just by considering my knowledge base. I have to consider the other agent's decision and then I can make my decision. That is multi-agent system. But if I can make my decision without considering your decisions, in this class you can consider this one as a single agent system. Because I don't have to depend on your decisions for making my decision. There is no strategic relationship between you and me. So then it is just straightforward. You can consider this one as a single agent system and design me as a single agent. You understand that now? Yes.
One question though.
Yeah.
So to try to sort of put that into a context.
Yes.
If you have a chess computer playing against a player, the chess computer could calculate the most or best possible move every single time, but not necessarily consider what the player would do, and therefore be a single agent in the system. But it could also be considered as a multiple agent system, because every single time you can calculate the best possible move, it's also based on the move that the human thing made.
let me explain this one in this way. Say you are writing a program for chess playing only. Simply, you are writing a program for chess playing, nothing else. And the computer is your opponent. You will give a move, computer will give a move. Or just you will give a move, another person will give a move. Your program will give a move. Now, in a single agent system, your program is not considering what is the move of the other person that much, or what will be his decision, something like this. Your program is just forwarding this one now, and then forwarding that one now, and then forwarding that one now, whatever is happening. Then your system can still run. But will that win? The answer is maybe no, and it is less probable because it doesn't have any intelligence that much. It of course has some intelligence, it is giving the movements and something like this, but it is not intelligent enough to win the game. Because the other person, even a simple human being who understands, just know how to play, maybe can give better move. Because I am putting one of my soldier in one place, just the program is putting, the other guy is killing that soldier, and I am just, without considering that I am moving another one. So then it is very difficult to win that game. But now you consider this one as a multi-agent system. So you are depending on his decision to make your decision and try to find out a better decision. Then actually it is a better chance for you. So in a multi-agent system, you are depending on the other agent's decision. In a single agent system, you are not depending on anything else in the environment as a dynamic thing. You are just thinking that okay, those are the things which are static, or in static states. Dynamic means it can be dynamic. For example, you can move these tables from this place to that place, but maybe those are static things. I mean there is no intelligent agent, and you are not strategically depending on those things. You are just mathematically calculating and then going there. So every agent may have some uncertainty part, and when you are a multi-agent system, then you will have to consider the uncertainty from your part and also from the other agent's part. So you cannot actually predict what they will do or that other agent will do. That is the complexity in a multi-agent system. And actually we may have a bit more understanding about multi-agent system or how to compete in multi-agent system later on, maybe not in this class but in another class. Until now, this is the idea that in a single agent system, we are considering that the agent's decision is not depending upon any other's decision in the environment. In a multi-agent system, the agent decision is depending of the agent decisions of some other agents. That is the idea. So can you move?
Yes.
Yep. Then the last thing is learning and rationalism. So when you talk about agent, then the question will come, where the knowledge of that agent comes from? Knowledge can be given or knowledge can be learned from experience. For a teacher, knowledge can be given or knowledge can be learned. Which is true? Which one is true? For me here in this class. Yes?
So assuming that you didn't exist before the class, then knowledge is given.
So knowledge is given if I do not see the class before.
Yeah, you did not exist before.
Okay, so normally what is the understanding? Is my knowledge given or is my knowledge learned from experience?
But your knowledge about how to teach maybe learned from experience.
Yes. But some knowledge given?
Why are you talking about whether you are giving knowledge?
No.
Yeah,
Knowledge is okay. Just what do you think?
I think the chess example would be better in order to explain this, because if you teach like the computer to play a move depending on what the other person played. So if he plays this, then the better move, like the best move, would be this. But if you let the computer play multiple games with
Yeah.
the player and then learn from previous games, then you play like this first, this second, and then maybe he'll figure out the correct one.
Okay.
So
I
this would
don't
be
know
a-
whether every one of you hear about his comment, but this is the understanding. I'm switching the example from classroom and me to a computer game. Knowledge is given. It means, for example, in the chess playing, you gave some mathematical calculation that your computer program will do to move to go for the next move. This is one way of making your system. Another way is you have given some mathematical calculation and rules within the program. Beside this, you make some other programming things in the program so that it can learn from the experience. I mean, when it is playing with somebody else, it is storing some experience in the memory, in the database. And then next time when it is trying to make the move, it is exploring its database what can be the best move. I mean, last time it may be lose for one move, then this time it will not make that move again. Kind of reinforcement learning, we told that. The agent will act something and the environment will give it a feedback that, okay, you lose or you win, something like this. But anyway, when you are putting the knowledge in terms of maybe program coding or something like this, it is given knowledge. But if you are saying that after playing something, it will improve, the program is improving from playing because the program is memorizing the states, what is happening in the game, then actually it is learning. A human child, for example, is the knowledge given or knowledge learned? For a human child. We are human beings and every one of us was child. Then our knowledge is given or it is learned? It is learned.
Both.
Both. Why both?
Well, you, like for instance with anything you are taught at school, that's knowledge that's given, but you also take the knowledge and try to use it in experience, like what we do here in radiology. We try to use the knowledge in our project work. So we learn something and then we use it in practice, which is learned from experience.
Yeah, but then what is given?
Then that's the stuff we learn at the course. For instance, in statistics, when we learn how to, like, what does this method do, we learn what it does, and then we go out and use it, we learn about how it works in that sense.
Okay, good point.
I'm just going to clarify that. Knowledge is, when we say knowledge is given, that's given directly to the system that the system doesn't have to learn themselves, like by doing mistakes, for example.
Yeah.
Is that true?
Yes. And if you compare your argument and his argument, then we are getting that you are telling that when we are getting some lesson in a class, that lesson is actually given to us as knowledge. But his argument is, as we have to learn that lesson at the end, so it is actually we are learning from experience. So it is not given directly. But anyway, do you want to say something on that?
Yeah, if that's the case, does it then mean that any like actual knowledge that we have can never be given because we're not a system? You can't give us knowledge like that. You can't inject knowledge into us. So the only knowledge that's given in our sense would be bodily functions and everything that our bodies does.
Yeah. What do you want to say?
Say that it's an interesting perspective, but in that sense, there would still be some knowledge that is given, but not by necessarily like someone gives it to you, but it's given to you by your genes, in the sense that you may have an understanding of what a red color is. You may not know that it's called red, but that's a different knowledge you have to experience and learn, but you know what red is in that sense, if you're able to perceive that.
Yes.
So as long as you're able to perceive something that's hardwired inside the brain, that would be knowledge that in some sense would be given, but you'd have to be able to genetically engineer that first.
Yes. So that is the idea. Now, when for human being, we talk about genetically engineering some knowledge inside of the human being to consider that was given. For computer agent, when we talk about artificial intelligence and artificial agents, we always talk about computer-based agent or something like this. So for computer agent, actually, some knowledge we can put in its program directly. If you see the temperature level is 3, turn on the heater. Something like this. So,
What did you say, Zoe?
if you see the temperature level is below 3, turn on the heater. For example, so you are writing this one exactly directly in the code. So that agent know how to make the decision and how to perceive the thing and then how to make the decision on that one. But some places you can say that, okay, You do not decide on temperature level 3 and then turn on the heater. See temperature level and see that the human expression. If they feel sad, then increase the temperature, something like this. So now how it will learn that the people are having a bad mood or they feel sad or something like this. Then it is, for example, deciding a facial expression based system. Going a bit more, let's say you are telling that, okay, in one place it increased the heater or turn on the heater, but people's sadness didn't go out or something like this. And people may have a button to tell that whether they like that intelligent architecture or something like this. They gave a negative push. Then the agent is learning that based on this kind of sadness movement, if I turn on the heater, still it cannot make the situation. It is learning, for example. So these are the learning things. We can learn, and some knowledge we can get as given. For example, human baby. If you see that a baby, we don't teach the baby how to cry, isn't that? But this is an action also baby need to do. We don't really teach the baby how to cry. And then some other things also baby do intentionally. Or we can still argue whether they are intentionally. Actually, poofing is not kind of intentional thing, maybe. But if you put a finger on the baby's mouth, it will start to, what is that word? Swallowing? Swallowing, okay. So it will start doing that one. How do a baby know this operation, this kind of action to take? So in any case, normally overall concept is human knowledge is learned from the experience, except those few exceptional examples where we can argue how they got these things and whether we will consider those things as learned or given knowledge. But normally we just consider that human knowledge is learned from experience. An intelligent agent, when you give something in the code and give something as a knowledge base which it didn't learn by a learning mechanism, we tell this one as a given knowledge. For example, you learned that one by another agent and created a database and then put database in this agent. Now, for this agent, this is just given knowledge. And then maybe it will learn more. So what is learned knowledge and what is given knowledge? It is just simply different in that way that given knowledge is we didn't learn. And the learned knowledge is something we are getting from the experience day by dealing with the environment. And then we can go for limited rationalism. In any agent, when you go for, the way you see that when I'm asking you something in the class, you are arguing something. And in some places, we see that actually we cannot get a one fixed rational point. If I say that is human knowledge given, somebody say yes, and somebody will say at the end of the story, somebody will say that no, still I think that it is not given only. Or it is everything learning based on experience. I mean, there is a debate always. So when we talk about rationalism, it is not exactly perfect always, that we know exactly this is the thing. So when we don't put our logic system fully that, okay, this is the only logical thing here to go, then we limit the environment, we assume something so that we can still make a decision. Right now, if we do not make a decision that, okay, the human knowledge is learning from experience or it is given, then for intelligent agent thinking, you will face problem because you have to decide which knowledge you will give and which knowledge it will learn from the experience. In any case, you have to put a rationality behind this, why you are putting that. And now in the rationality's case, you have two options. One is perfect rationality, another is bounded rationality. When you give a knowledge base to the system, to the agent, then based on the knowledge, it will make the decision. And perfect rationality is the agent can determine the best course of action regardless of resources available. It means that when it is coming to the logical decision, it will always take the best decision, even though the resources are not available. How it can take the best decision even the resources are not available? You can see this kind of example in Google Maps. if you go, for example, from Aalborg to Copenhagen, it will give you option for walking, for biking, or for car option, or even for plane option also, airplane also. It can give all these options to you. Then maybe for car it can say you that which place have toll and which roads have toll and which road doesn't have toll. So it is giving you many information. So what is perfect rationality? Perfect rationality is, regardless of resources available, it will give you the best decision. For example, Google Map doesn't know whether you have money for toll or not. Google Map doesn't know whether your car is speedy enough or not. But Google Map knows some other information. And it just want to give you the best possible route or the fastest route. Maybe Google Map can still give you the fastest route regardless of you knowing your matters. How do Google Map do this one? If you consider Google Map as an intelligent agent, how do it do this one? Because Google Map makes some other assumptions. And as I'm always remembering you, all these things you are learning just to make good assumptions. So Google Map is taking some assumptions, yes.
So the point is that just because Google in general can observe a broad amount of data about you as well, it can also use that to perform some meta-level rationalization that would help perfect its algorithm or its decision towards having a perfect rationality towards you.
Yeah.
In Google Maps specifically.
Yes. It is taking some other assumptions also, beside those things. Here is, when we are considering bounded rationality, the way Google Map is working, it is actually kind of bounded rationality. The agent must make good decisions based on its limitations. That is the real thing happening here. But if hypothetically, if we consider that Google Map is working in a perfect rational way, then we have to expect that without caring your speed, car condition, without caring your pocket condition about toll, it can give you the fastest route. Because regardless of resources, it can take the best decision. For example, a robot is measuring the distance from the coffee room to my room, for example. There is a stair in one place and there is no stair in another place. Robot cannot follow the stairs. And you are trying to make that robot. Then, in the way there is a stair, maybe the distance is very short according to the map. But the way there is no staircase, maybe the distance is longer. Now, if you tell the robot to decide which way it should take, which will be the fastest way to take, then the robot can decide that the way which has corridor by thinking that I do not have the ability to use the stairs. On the other hand, robot can decide that this is the fastest way, taking the stairs. So when robot is deciding that this is the fastest way, taking the stairs, even though it cannot actually follow that route, this is we are telling as perfect rationality. And then when the robot is taking the corridors, because it knows that it cannot use the stairs, and based on its limitation, it is taking the decision. We are telling this is bounded rationality. Actually, human society is also like this. We always tell that if somebody is trying everything perfect, it will not happen. Something like this, and it makes chaos actually. Yes.
So you're saying that bounded rationality is just perfect rationality, but with some sort of limit. So in Google Maps scenario, it would be
Bounded rationality is not perfect. Bounded rationality is addressing the limitation which perfect rationality is not addressing. Which is the fastest way? It is of course the staircase. But which is the fastest way for that agent? The agent cannot take that staircase. The agent needs to follow the corridor. So for the agent, it has limitation and it is considering the limitations. So according to rationality, okay, that is the fastest. This is the shortest route, maybe, but that shortest route we cannot take. We have to take another route. We have to take another route, and that's how we have to make a boundary of our rationality. Of course, it is logical to decide that this is fastest, and the robot can argue with you. Why you are telling that I have to take the corridor when you always tell me that to take the fastest route or shortest route? The corridor is not the shortest one, staircase is the shortest one. So then you can argue with the robot that you don't have the ability to use the staircase. You know, sometimes in comedy movies, what we exactly see? Somebody is telling something which is looking very real and then very logical, but you know that is we don't see in the common behavior. So that's why we laugh about that. Do you understand that? If you can consider comedy movies or something like this, the comedy behavior, how people use those things. Yes.
So the point is, or the takeaway is that it's not one version that is more logical or better than the other. It just depends on the situation and what you want to get out of it.
Yeah. And then when designing an agent, we have to be careful about looking like this. Because as a designer, this should be in your mind that it is not the perfect rationality we want to get. It is the bounded rationality, and we want to get the optimal result from the bounded rationality. So this is all. As I told you that this list is not limited. I just give you some concepts related to intelligent agent designing. I mean, how to understand the environment, how to understand the agent architecture, something like this. These are some of the concepts. And just one example before the break, that is human dimensionality of complexity. I mean, how human being we can consider. I did not put those things in red color. I mean, I put the color, but I did not decide those. This is from the reference, the book I have given you in the last lecture. So that is from the reference. If you consider human being as an agent in this world, we can see that a human being are mostly hierarchical, and then we can see that they have indefinite stage and infinite stages, and then the overall observation capacity of a human agent is partial observability, not full, and then it is stochastic, and then it works in a multi-agent system, and then knowledge is learned, and by assuming that the child knows something, maybe this is also learned. You can assume that one. I'm not going for that debate again. And then bounded rationality. Yes?
You mean flat up there, right?
Yeah.
Good.
Oh.
You should wrote fat, and that doesn't mean.
Any human being always have fat, isn't that so?
Yes.
So, you can have. Do you have any question? Then have a break just. Okay guys, we are going to start again. So first we will watch two videos. One is example robot, because we are talking about this one so much. I think you already saw, many of you maybe saw this kind of examples. Just see one more time. And then a more relevant one to us. I mean, in an academic scenario, when you do a small project, you don't normally go for this kind of commercial things. So we go something which is more doable to us in this environment. So we'll see an example of that one also. And then I'll go for the discussion again. First one, this one. Okay, wait. what do you feel about this one? The man was touching the hand side of that robot. Why? Can you understand that? Yes? Just say it, no problem.
To indicate it's finished.
Yeah. But is there any other way to solve that one?
They could have placed a weight.
Sorry?
They could have placed a weight, so you could sense for the tray that can take them.
Okay, but for example, I'm taking this and then it says that okay, it was taken. So what will happen?
It's like,
Hold these.
Or you can introduce a bias where you wait for a couple of seconds after.
Yeah, these are the things. While designing the things, it will always come into our mind that how to do the things done. So for this robot, you see this is a commercial implementation, but still they didn't put that facility here. They just put simply 2 buttons in 2 hands, and then you can touch this and then it can see that okay, it's finished and then it can go. And also the way it is tracking the roads and all these routes and all these things, that is also, you can guess how the agent is working here. Then the next thing.
Restaurant, there are 4 tables, table number 1, number 2, number 3, and number 4. As kitchen, robot is now available to serve, and this is our application.
So you can change the setting to the right IP address for the robot that we want to control, then press connect. Let's send the robot to table number 4. Once it receives the command, the robot will start moving and then start driving to table number 4. Once it arrives at table number 4, it will wait until the customer to remove the food trays to move again. Now I remove the food trays and it will start moving again and going back to the kitchen. While the robot is moving, the application will show that the robot is not available. Please wait. And now that the robot is driving back to the kitchen. Once it's back to the kitchen again and turned around, the application will go back to its main page and it shows the robot is available again. Let's send the robot to table number 1. So now the robot will not move since I haven't put the food trays on. Once I put the food trays on again, the robot will go to table number 1. And table number 1 has a curl pad. It's just to check that the robot its ability to follow the line. Once it arrives, it will wait until the customer to remove the tray again. Now I remove the food tray. And it will turn around and go back to the kitchen. As you can see, the app shows that the robot is not available right now. Now it's back to
Problem and solution. While we are telling that design an intelligent agent, this is the problem. Design an intelligent agent. You know the problem now. And then you have to understand the domain, you have to understand all the assumption things, and then you are going to make a solution at the end. How will you do that? There are so many things which you cannot get a specific answer from the people who are telling you to design the robot or design an intelligent agent. So there are many unspecified things for which you have to make the assumptions also. And how will you make the assumptions? The main thing is this one. Common sense reasoning. Is that clear? Common sense reasoning.
Is it any different than what we think it is?
No. I'm just giving some time so that you can put this one in your mind. And then whenever you design something, you will always need to think in this way. What is common sense? And just apply that one. If you do not have any specification for something, But if you have a specification for something, then you should go for that. Because I don't know whether you saw that video or not. There was a video in maybe in YouTube or Facebook. I cannot remember where did I saw that one. In that video, somebody is telling that I need a straight line, but it should look like a kitten. So and then it is engineer's job to do that. And then engineer is asking, how can I do that? It can be straight line and then it can be a kitten, something like this. So. Well, at the end they are telling that you are engineer and it is your job to finish. It is not your job to ask, or it is not your job to argue with us about these things. The way we are saying, you just have to deliver us that one. So sometimes it is the case. When you have something specified, do not go for argument or do not go for assumption. Just try to implement that one. But well, it is. For making fun it is possible, but practically not possible. So we always have this one, common sense reasoning, to design something. And then we are making a solution for an we want to get a service from an intelligent agent, and I am telling you to design that one. So you are understanding the problem, and then you are giving me a solution. And then we can consider that solution is an answer. Okay? But that can be it can have many different kinds. It can be optimal solution, it can be satisfying solution, it can be approximately optimal solution, it can be probable solution. Do you understand these terms? Because these are actually just normally English term. I think you can, the way you perceive these things, that is actually the explanation for this one. Optimal solution is the best solution. Best solution by considering everything. That there cannot be anything better than this one. Whatever amount of funding you can give, whatever amount of resources you can give. This is the best one. And then satisfying solution is, this is not optimal. Maybe. But I am telling you to give me this kind of agent and you are giving me that and I am satisfied with the performance. Maybe it is not the best. Even maybe you are not using all the resources. For example, you will see in some of the security systems, they are using some kind of processor and computing system, computing power like this laptop, which has kind of latest processor for that laptop PC and something like this. They are using this one only to take a passport photo. And government are buying those kind of system and employing those systems in many different places. So you may argue that whether they are using the whole what can I tell you? They are using the whole exploring everything on that resources. Maybe the answer is no, they are not exploring. But their specification is like that. And they told that this is the system solution I am giving to you, and this is the price. And maybe the organizations are buying that. But it doesn't mean that it is exploring every possibilities of using all the resources in the most efficient way. So it is a satisfying solution and that's why I am buying. But it doesn't mean that it is optimal solution. Then we have approximately optimal solution. This is approximately optimal solution we use when this is optimal based on these limitations. We have limitations, but based on these limitations, this is the best way. Nobody can do better than this. But the optimal one is that we do not have any resource problem and everything. Whatever you give, this is the best. There is no limitation because of funding or resources. This is the best. You cannot go for that. For example, electricity speed, you cannot exceed for that. Even if you fund more, it will not increase the speed of electricity, isn't it? Or the speed of light. So if you make a cable which can transfer data from one place to another place, that cable cannot be faster than electricity or light, isn't it? So that is the thing, that is optimal solution. Satisfying is when I am satisfied, even though you are not using the resources fully, or you are not giving the best performing system. Approximately optimal solution is considering the limitation and then giving the best one, based on the limitations. And the last one is probable solution. It means that there can be many solutions, this is one of the many solutions. So finish then. When considering the solution, you can keep these things in mind. Then we are preparing a solution. We want to make intelligent agent. Actually, what we will do, we will make some computer program and some instruments making, and we will put these things in computer, isn't it? And then actually this is kind of representation. You can see what will, how we will proceed through developing that system. I mean the implementation of the system. We have problem and we have to reach the solution. Then we have high level specification. Then we transfer the, I mean the overall idea, what are the conditions here. And then you put this one in programming language. And then program transfer this one in assembly format. Assembly transfer this one in, assembly means the binary object code. I mean which computer can directly run. Because when we write a C code, it cannot run directly. It converts this one in binary code, which we call object code. So this is just converting into object code and then going to digital circuit, and then it is actuating the thing. Actuating means showing the actions directly. Now the basic idea about the agent. What are the parts of an agent? If you see the just consider this one as an example for our serving robot. Okay, serving robot. It will have controller and it will have body. These are the two basic things. So, and it will work with the environment. This is the overall architecture of our agent. If you go a bit details on that one, then you will find something like this. It has body has hand and everything so that it can actuate the actions, and then also it may have some sensors in the body. But then controller will take the sensory input and perceive something, and based on that it will put some command on the body, and then body will act with the environment. And when controller is perceiving something and giving command, in that time it is taking help from the memories. And these memories we are telling as we can provide to the agent as knowledge base. This is the overall idea. So when controller is deciding something, each time we have two questions. First is it is asking itself, what should I do next time? And then also, what should I remember from that? So that its memory can increase time to time as an intelligent agent. You understand that? Its memory needs to be upgraded time to time. So it will remember something, what it is doing, and then also it will just do the things. Make the decision, and then based on the decision it will learn something for future use also. So as I told you that the memory is actually kind of knowledge base we are giving. So what it looks like, a knowledge based system architecture. This is mainly this one, this red blob here. Not exactly, this is a blob, binary large object. So this is blob, yes. So here, we have knowledge base, we have inference engine, and then we have user interface. I mean, so that it can, the controller can give something and take something. So these two things is actually making our memory. One is knowledge base, another one is inference engine. These two things actually making not memory exactly, making the intelligence. So while I am telling that these two things are making intelligence, can you understand that? How? Why we are intelligent? Human being. Why are we intelligent? Me, why? Okay, you may disagree that okay, Mohammed may be not intelligent. So just take another example. Yes.
We are intelligent because we can draw conclusions or decisions based on knowledge that we've learned or the knowledge that we have.
Okay, good. I think I got it. Yes. You?
Yeah, second.
Similar thing.
Yeah.
So
We can reflect on our actions.
we are talking about two things. One is we have some knowledge, and then we can take some decision based on that or reflect on that, something like this, isn't that? So here actually those two things. Inference engine is doing the inferencing, I mean taking the decision based on the knowledge. And this is the knowledge base. Every single action we are doing, that is coming from inference engine. The engine is giving through the user interface to us that do this action. And then I am doing this action, and then based on my stimulation and then sensors, it is taking some feedback and putting some knowledge there again. And day by day, my knowledge base is increasing. That is the idea. Here is another thing. When you talk about knowledge base for human being, what is that knowledge base? Knowledge base is just kept here, isn't it? And what is this? This is just neuronal circuit here. We have neurons and then we have some connections within the neurons. This is just some kind of circuit. If you take one single neuron, then it is taking some input and then it is giving some output. And that is how we design artificial neural network in computer. With that concept. So these kind of neuronal elements, actually all of them are taking something, giving something, kind of intelligence. It is true. So is there any knowledge base? The answer is there is knowledge base. Knowledge base doesn't mean that you have to have a big thing. Even the way you are changing the state, this is a knowledge. Flip-flop in electric circuit, do you know that? Flip-flop in electric circuit.
The switch?
Yeah, switch or something like this. It is, in digital circuit you will get something. In memory, computer memories we use this one. Or say for example transistors. So it has some property. And those property is giving it some kind of, it is showing us some behavior because of that property. And it is already put in there, and that is the knowledge for that one. So if we go for that kind of atomic version of the things, what is intelligence or what is knowledge base, then we will actually get these kind of explanations. But if we look into the bigger picture is that we need a knowledge base and we need an inferencing mechanism. Inferencing means making the decision. Okay? So we have to have these two mechanisms. And if you think one single neuron, it also has those two things. One is it is saving some state or behavior. Either it is saving or it is naturally made in that way that it will show that behavior. So that itself is a inherent knowledge put on there. So we have both of these, knowledge base and inference engine. So while creating an intelligent agent, we have to put both mechanisms. We have to put some knowledge on that one so that it can make the decision. But how it can make the decision, how it will read the knowledge, that is the inference engine. For example, if you say that, okay, for serving robot, we consider about the weight things also. So we can put the knowledge that the weight threshold will be, for example, less than 100 gram if there is nothing on its hand. Actually, it can be 0 gram, it can be 10 grams because of some noisy elements. But let's say it is less than 100 gram. So if it is less than 100 gram, it will think that the hand is empty now. But if it is not more than 100 gram, it can think that I am not free yet. So if somebody take the tray and put the hand on it and press this one, so still it can think that I am not free yet. In that way, it can work. But here, what is the knowledge base and what is the inferencing thing? The knowledge base is I am giving it the information 100 gram to measure to distinguish between the situation. And also, I am giving the logic how to distinguish between the situation. That it will compare 100 gram whether what is its weight and then 100 gram. If its weight is, the weight it is getting from the hand is higher than this, then it will make one decision. If it is lower than this, it will make another decision. That is inferencing. So everything actually in an intelligent agent we are putting. That is the thing. So how knowledge is represented. Actually in this course, when we are talking about artificial intelligence programming, so far IC media technology is a very application oriented subject. So you don't need to go in depth of every single thing right now. But I'm just telling you an overall idea, how the things are happening. When you consider about knowledge base, normally we represent knowledge base like kind of semantic network. semantic network. And if you ask me what is semantic network, the concept is very easy. Can you remember the concept of ontology I told you last class? Ontology. Ontology, yes. Those who read about philosophy, they know this one very much, I think. But for easy explanation, ontology is just giving a class name. I am Muhammad, he is somebody, he has X, he is Y, he is Z, for example. We are all individual persons. But then what is our class? Our class is we are human beings. When you put a word human and then put some description that what is human, then we are telling that we are setting up an ontology here. I'm just telling the practical meaning of this one. What does ontology means, just to realize easily, okay? So here, say for example, we are considering about a laptop computer or just a computer. Then the question is coming, what kind of computer? We can say that, okay, computer and then kind, it is laptop. And then computer and then name, or the model number, we can say, for example, this is this model number. And then we can say computer, and then what is its brand name? We can say this is Lemon Computer. Computer, and then say who is the owner, maybe we can say, for example, here, owned by Craig. And then computer, in which room it is set up, we can say that there is a room in this place. So we are defining a term computer, and then we are defining its different attributes, and then we are putting the values of all those attributes. This is the way knowledge is represented. And how it is a semantic net. When we are talking about semantic net, the term, this one, how it looks like. This is actually a semantic net. Where you have ontologies, related attributes, and then you are talking about some example values. Giving the values always not necessary here. Just defining some classes, it is the main thing in semantic nets. This is another example of the similar thing, not same. This is another example. But they are not same. And what is the difference between these two things? The main difference is this one is more organized than this one. How it is more organized? It is defining the classes and then clearly showing the relationship. When you look into this one, it will be difficult for you to find out those kind of concepts very clearly. So a semantic network, how will you define? It is your choice. But there can be quality differences in drawing those things. Yes?
Would you then say that in order to properly utilize the type on the left from the type on the right, you need a high level of abstraction built into it?
Yeah. When you read about object-oriented programming, you will see that there are two concepts, level of abstraction and level of details. So you are actually mentioning that one, how we are abstracting the concepts. So this is one example. They are basically meaning the similar system, but we can say that this is more organized. And how we put these things in computer program? We have semantic net like this. We define the concepts like this. Our robot agent will have hand, and hand will have these kind of attributes, and it will have, maybe you can just go further details in a hierarchical notion. So when you go all these notions, then how will you define an operation for that agent? For example, this one. In computer language, you can go like this. It is in high level language. We are not mentioning which language. We are just telling that this is logic programming or something like this. So you can say that the computer number 2347, we have computer number 2347, and then the attribute is owned by, and what is the value? Value is Craig. I mean, the Craig is the person who is the owner of this computer. In this way, we can save this knowledge base maybe in the computer in a database. I don't know whether you see any database structure. I mean, created in Access or Excel or Microsoft SQL Server, something like this. We normally put databases. We normally deal with databases like these kind of operations. We put a value in the database like this, and we can ask the value from the database, and it will come back with these kind of attributes, something like this. So the reason I put this slide here, It's just to give you how knowledge, tell you how knowledge is represented in a system. So do you understand something from this? I would like to tell a bit more about this one. Ontology and knowledge base. So in ontological description, we actually define individual classes and properties. Individual classes and properties. Just see here. The class is a computer, for example. And this computer is an individual in computer class. And then this is a property. And this is the value in that property. This is the way we see the ontological details of a semantic net. So, and you can get a good example of semantic using this kind of semantic net and these kind of concepts in semantic web. If you search in Google, you will get a lot of details about this one. What is semantic web? It is just a proposed development of WWW system, I mean the World Wide Web system. When you read something in computer, and then the way, if you see the word Windows, for example, the way he understands the word Windows, the same way you understand the word Windows, I understand the word Windows in the same way. Though we know that Windows means something like this one. But in computer operating system, if somebody writes Windows, every one of us will know that this is not this window. How do we know that? Yeah.
Our knowledge of the world.
Our knowledge of the world. We know that this is not this Windows. But for example, a computer is reading the text. You have written in some place. How the computer will know that this is not this window, this is operating system Windows? I mean, we human beings can understand that is operating system Windows. How computer will know that? Because computer can think that Windows means this one, but actually we are not meaning this one in the text. We are meaning operating system Windows, for example. Yes?
Well, we are technically applying implicit attributes to the Windows when we think about it, so just be to apply these attributes, I guess.
Yeah. You?
Well, we can make assumptions based on context and other words nearby.
And how many assumptions we can make? At the end, the thing is, we have to have a knowledge representation technique, which computer can understand. We have a knowledge representation technique within us, and that's how a child is learning things and then putting in his brain and then working in this world. And then we see that the way one child is growing up, at the same way I have grown up. And then we are not having that much mismatching in this way of doing the things. So computer need to have a way, and that is semantic web. In semantic web, the idea is everything in the web we will define with ontology, with the class and attributes in a structure so that computer can read the things and understand the things as we do the things. That is the idea behind semantic web. Is that complete? No, because it is continuously increasing. Everybody is adding new ontologies and then it is just expanding. But the more it is expanding, we are going to maybe nearer to the way we human beings understand. This is semantic web. And then when we are creating knowledge base, if we have multiple knowledge base, for example, human also have a knowledge base. Computer has another knowledge base. And then in computer also, for example, philosophy has some kind of definition of some words, but computer engineering has some other kind of definition of the words. In architecture engineering, they have another kind of definition of words. In architecture field, if you say window, they will understand this is this window. But in computer world, if you say Windows, they will understand this is an operating system. In food menu, if you say Apple, they will understand what is Apple. But in computer world, if you say Apple, everybody will understand what is Apple. But these ontologies are not same, because we have two different knowledge bases. Then we have to have a translation method between these two knowledge bases. And day by day, we are actually developing those kind of techniques to get a semantic web where computer can actually contextualize the sentences in that way. From which place it is coming, how it is coming, and if you can remember, in the last class we saw that in text mining, we can try to realize, even from the text, which time the president gave the speech, United States president gave the speech, depending upon the words he have used in his speech. So how can we realize that? By contextualizing the sentences and words. That is the idea. So knowledge base, this is actually giving us the intelligence with the inference. And what is knowledge base? Basically this is just a collection of ontologies. And what is ontologies? What are ontologies? This is definition of individual classes and properties. That's all. And if you want to see an example, you can just think hotel ontology. I mean, what are the things you can get in a hotel? You get hotel room, and then different kind of rooms, bathroom, standard rooms, suite rooms, only something like this. All these things is a class. Then you can have some values for this one. For example, for room class, you will get room number 114, 115, something like this. And then each room then have its own properties. That is the way knowledge is represented. And then when you have knowledge represented, and we are going to implement this one in a computer, I'm not making the change between the previous slide and this one. I'm just giving this concept to you directly as a separate concept, but you will have some linking between these things when you work on this one. I mean, your brainstorming will help you to understand the link, okay? This is finite state machine, and this is kind of the last concept today I'm giving you as the. What is finite state machine? Say for example, we have a vending machine here, Coca-Cola vending machine or something like this, drinks vending machine. You have some in the ground floor. So, I come here and it is locked. I press the switch to get something, but nothing is coming because it is locked. Then I put a coin. So I put the coin, this operation. And then when it got the coin, then it is going to be unlocked. And then I am getting something. And then if I press again, what will happen? It will go locked again. It will not give me anything again. But if I put coin here in its unlocked state, then it will give me service again, something like this. So the way I have represented the whole system there, can you get the similarity? The service you can get in the downstairs, the vending machines. Are they similar like this? Maybe not exactly, but similar, I'm telling, not same. So when you have this one, it is very straightforward that these are the states of the system. It can be locked, it can be unlocked. And then there are some operations on those states. One operation is pushing, another operation is giving coin. Two operations. So this is the way we are defining a system. And then in computer, what can you do? In computer, in object-oriented programming especially, as you told that we have data and then we have some processing. So data, you can consider the whole database and everything is a state. And then you are doing some processing on that. So this state machine model is actually very nearer to our direct coding or implementation. So that's why when designing a system, we generally try to make a we generally try to define the system in a state machine model. So and when something do an operation, it is we are telling as automaton. Finite state automation is like automaton is just like this. For our robot case, you can make some figure like this from the robot case also, serving robot case. And then we can directly put those in the coding based on the conditions and all these things. Yeah, that's all. Good, then we will see another video now.
Can we turn down?
So this is Compass being started up, the editor where you can put together a factory layout. I have the scene already saved as a prefab, so you can just drag it into the scene and the whole thing will build up. So it's just a basic scenario with a couple of conveyors, machines, agents, and storage objects. Here on the left you can see like a hierarchy of the scene, how everything's organized. You can also select stuff there. And in the bottom part, you can now see the selection of objects that I put into the editor. You can just drag them into the scene and assemble the factory layout or virtual model of the factory that way. And right there's the properties view where you can edit data and the behavior objects. This is now already in Unity. Upon startup, it will import the scene that was created in Compass. And when the simulation will start right now, will see how material is getting created at sources that have been defined in Compass, and yeah, you can see the material being transported on the conveyors, and the workers will start fulfilling their tasks as it has been defined for them in Compass. There you can also see the visual hints that will show where problems are. So you can see there's a malfunction occurring right now where the red colored agent is repairing it, and the yellow signs show that there are block objects that material cannot be forwarded at the moment. There are also robotic agents, but basically it's just another 3D model. It's more or less the same implementation for these guys. Yeah, as you can see, they are sorting material based on what it is, and yeah, as said, all of this has been defined in the rules. So here we have an agent who's like working at a workbench, he's like producing parts there, and the robot is supplying him with material input. And yeah, right now in the middle you can see that there's like a bottleneck where the whole thing is kind of blocked, and these are like the things that you can identify with the simulations. So here the simulation has been reset, and in between simulations it's possible to change stuff in Compass. So you can rearrange objects, rotate them, move them around, and you can also change the properties of things. So you can change the speed of a conveyor, for instance, or the speed of the robot, or processing times, all of these things. And that back in Unity, without having to restart the application, these changes will carry over. And as you can see, the conveyors now transporting stuff faster, and the agents are automatically factoring in the new positions of objects, so there's no need to manually interfere with that. And you can also move stuff around in Unity. As you can see here, you can rotate and move objects, and the agents will immediately, in real time, react to these changes and adapt to the new situation and move to new places.
Okay, so this was just an example. So how many agents there, intelligent agents there? It is very good.
It depends.
It depends anyway, no more explanation. It depends, right? Actually here you can see that, okay, that car is on the robot maybe. If you call about robot, okay, if you call for robot only, but these human beings are also intelligent agent. Every single machine can be intelligent agent. If I tell you to make an intelligent agent, just simple intelligent agent in Unity, you can just draw something like this in Unity and then show some behavior and then control those behavior based on some knowledge base. Do you understand that? I mean, it is not a big thing here. Because here every single thing can have some kind of intelligence, and you can put those intelligence in this design. So we will learn this one eventually. In this class, my assignment is not like that you have to do this one right now in Unity and Python, but that is the idea we are going for eventually, okay? You will have some communication with Python programming language and Unity design. You will design something in Unity, and then you can give some command from Python. That is one way of doing or learning how artificial intelligence programming will work here. Okay? Yeah, this is one example. Then I have this one. The state machine model we already discussed. I mean, this is finite state automata. Okay? Then we have this guy Maurice. He is looking for gold. gold mining, and then he has some attributes: sleepy, thirsty, hungry, whiskey, and gold. Okay, and our target is, and for all of these, when he is sleeping, then these attributes changes. When he is mining, these attributes are changing. When he is eating, these attributes are changing. Okay, some are increasing, some are decreasing. Our target is getting as much gold as possible. By keeping Maurice alive, and when he is dead, then it is finished. And when he will die, when sleepy, thirsty, and hungry goes above 100. That is the challenge. Now, how can you do this one? You can simply start by doing something like this. Defining the variables. This is not Python code, so just do it in Python. So this is the condition for you. He cannot die, and after 1000 iteration, what will happen? You can interpret this system. You can interpret this system in many different ways. My only objective is just to see in 1000 times whether he is dying in the first step or he is dying in the last step or he is still alive. Doesn't matter. The only objective is you have to reach maximum amount of goal, and I want to see which group is achieving that. Is that okay? Use Python while doing this one. And then the basic thing is you will implement the states of Maurice, and then you will define some functions to assign random transition from one step to another. I mean, just use some Python functions. It is just actually kind of introducing you with Python also, not only the logic things. And then calculate the accurate amount of gold after 1000 iterations. Actually, you will calculate this one in each iteration. So I'm just telling I want to see what you have got after 1000 iterations, and then present your implementation and outcome in graphical mode in 1 or 2 slides. I mean, you don't have to say somebody else. Just put your understanding. I mean, understanding means two things. One is the way you implemented this one. Just say that we have these kind of functions which are doing this one, or you can just draw a block diagram, finish. This is the way you have done this, and then you got this amount of code. This is without applying any kind of extra intelligence. And then try to do something intelligent from your own concept so that you can improve this one. And try to see how much gold you can reach. And then put that structure again in the slide. So you will have a presentation file where you will have 1, 2, 3 or 4 slides, where you will write where we can see that which method you applied to get those kind of code, those amount of code. That is the assignment. So you are getting until now 2 assignments. One is next class you have to present something, and then this one. So game over.